This section explains what statistical mechanics is. Complexity. You cannot track collapses into law the moment you stop tracking it. A single random walk is unpredictable, but the ensemble of all walks from one origin has a shape you can write in a line. That inversion is the whole discipline. Statistical mechanics replaces one intractable system with the collection of its similarly prepared copies, then reads the collective simple behavior where the individual's was hopeless. Temperature, entropy, phases, none of these live in a single atom. Each emerges as a property of the ensemble. This is what the chapter promises the rest of the book. Ignorance about the part, taken at scale, becomes exact knowledge of the whole. This section explains the core move that statistical mechanics is built on. Give up predicting the single trajectory. The collection obeys a law that the individual never does, and that inversion is the whole engine. Statistical mechanics computes the ensemble of similarly prepared systems, the entire collection at once rather than any single one, and the macroscopic regularities, temperature, entropy, pressure, fall out as properties of the collection rather than of any member. A lone, random walk is irregular and unforecastable. The cloud of all walks from the origin has an exact, elegant distribution. This opening chapter's job in the arc of the book is to plant that move, the intractability of the individual dissolving into the tractability of the many. It also names the instruments each later chapter sharpens: entropy, Monte Carlo, phases, correlations, and transitions. This section explains why a random walk is the book's minimal proof of emergence. Add enough independent steps, and the microscopic law governing each one stops mattering. Only its mean and variance survive into the sum, which becomes Gaussian no matter what you started from. That is the chapter's whole move. The random walk is the book's minimal proof that macroscopic behavior forgets microscopic detail. Diffusion, drift, and the spreading square root of T envelope are produced by the underlying randomness itself, not something that persists in spite of it. They arise identically across wildly different step rules. The central limit theorem is the fixed point everything flows to. Emergence, here, is detail subtracted under aggregation rather than complexity added. Every later chapter's order parameter and universality class is this same forgetting, seen again. This section explains why the random walk is the cleanest demonstration of a structural fact. A macroscopic law can be simpler than the microscopic reality it emerges from. Add up many independent fluctuating steps, and the sum forgets almost everything about each step. Only the variance survives. The root mean square distance grows as the square root of n. The endpoint distribution flows to the diffusion equation, and the path itself becomes scale invariant. None of this depends on whether the step was a coin flip, a molecular collision, or a polymer link. That is what universality means. The chapter is the book's thesis in miniature. Statistical mechanics is the science of what remains. After summation, washes out detail. The surprise Sethna plants is that gravitation itself may emerge this way in footnote 1, which tells you the pattern is not special to random walks. This section explains how temperature and equilibrium fall out of counting states instead of following trajectories. Give up on the trajectory. Chaos scrambles everything you knew except the conserved energy, so stop solving Newton and instead count. Declare every microstate on the energy shell equally likely. This is the microcanonical ensemble. Equilibrium becomes the most typical partition of states, a regression to the mean. Every quantity you called thermodynamic now drops out as a derivative of the log count, the entropy. The entropy S equals K times the logarithm of omega, where omega is the count of microstates. Two bodies sharing energy settle where the total entropy is maximal, which is exactly where the partial derivative of entropy with respect to energy matches between them. So define 1 over T as the partial derivative of entropy with respect to energy. Temperature is a conjugate quantity. The exchange rate of entropy for energy, pressure, and chemical potential are the same move against volume and particle number. This section explains how the randomness in a many-atom system becomes the tool that makes thermodynamics solvable. Chaos is the ally here. Newton's equations for n atoms are unsolvable, and once solved, useless. Chaotic scrambling destroys every detail you knew, except the one thing conservation forbids it to destroy, the energy. So Sedna's move is to stop tracking trajectories and hypothesize that energy is all that survives. The equilibrium state becomes a uniform average over every microstate on the energy shell, the thin band where the total energy H lies between E and E plus delta E. This is the microcanonical ensemble. This is the chapter's germ for the whole book. Thermodynamics is the geometry of that shell. Count its phase, space, volume, written capital omega of E, and temperature, pressure, and entropy fall out as how that volume responds to what you vary. This section explains why a single instant average over all equal energy states can stand in for a long time measurement. 2 facts. License the swap. The first fact is that the Hamiltonian flow is incompressible. Liouville's theorem. The flow stirs the energy surface but never compresses any region, so no state is dynamically privileged. All states are created equal. The second fact is ergodicity. When the flow is ergodic, the surface is one indivisible stirred piece with no invariant subregion of non-zero volume. A single trajectory visits everywhere, so its time average equals the surface average. The pattern underneath is this. The time average equals the space average, whenever the dynamics is measure-preserving and indecomposable. The surprise arrives in Chapter 4. Equilibrium here has no attractor to fall into. There are none. Transients merely become rare. This section explains how the 4th chapter earns dynamically what the 3rd chapter only assumed. Chapter 3 treated all equal energy states as equal by mere ignorance. This chapter earns that democracy dynamically. Liouville's theorem says that Hamiltonian flow conserves phase, space volume. Trajectories only stir the energy surface, never reweighting any region, so the uniform measure is the one the dynamics preserves. Now add ergodicity. The surface gets well stirred. One trajectory eventually samples all of it, and any observable's long-time average equals its microcanonical ensemble average. That equality is what equilibrium means. The generative primitive is this. An invariant measure plus mixing collapses the time average onto the space average. Every later result rests on this bridge. The footnotes escape hatch, take it on trust, and skip the chapter, marks it as foundation, the thing the rest of the book stands on rather than a piece of the machinery. This section explains entropy as a single quantity seen 3 ways. One number wears 3 masks, and the chapter's whole work is showing they are the same face. Carnot's wasted heat, energy that spread out and won't gather back, is the same quantity as the disorder of mixed gases, and the same quantity as your missing information about which microstate the system occupies. Here is the generative move. Entropy counts the microstates compatible with what you macroscopically know. Irreversibility, disorder, and ignorance are 3 projections of that single count. Times arrow, the smear of mixing, the bits you lack, read them all off. 1 logarithm. To predict the next instance, whenever a quantity refuses to run backward, look for the count it is quietly maximizing. This section shows how one number wears 3 masks. Entropy counts the microstates compatible with what you macroscopically know. The whole move of Chapter 5 is that irreversibility, disorder, and ignorance are 3 questions asked of that single count. Carnot's engine cannot beat the reversible limit because the count of an isolated system never falls. That is the question of irreversibility. The entropy of mixing and the residual entropy of glasses measure how widely that count spreads. That is the question of disorder. Shannon's compression bound measures the same log count as missing information. The generative primitive is this: fix what you know, count what you don't, take the log. Every face of entropy is that 1 count. Read under a different question. This section explains what a free energy really is, the bookkeeping cost of ignoring. Ignoring is a generative operation. A free energy is what ignoring costs you to bookkeep. Refuse to track part of a system, the heat bath that trades energy, the reservoir that trades particles, the atomic jitter beneath a moving object, the microstate inside a small volume, and you integrate those degrees of freedom out. What survives is a new ensemble whose entire thermodynamics collapses into 1 function. The chapter's organizing question is literally, what do we ignore? Each distinct thing ignored generates its own free energy. Ignore an energy bath and you get Helmholtz. Ignore a particle bath and you get the grand potential. The free energy is the minimal sufficient statistic for the part you kept. Forgetting the rest compresses rather than discards. This section explains the 1 move the 6th chapter makes. Ignore part of a system, and the part you ignored does not vanish. It condenses into a free energy governing what remains. That single move is the partial trace, given in Chapter 6, footnote 5. Sum away the degrees of freedom you refuse to track, and their statistics survive as an effective energy for the rest. Integrate out the heat bath and it returns as the Helmholtz free energy. Integrate out particle exchange and you get the grand free energy. Integrate out atomic jitter and you get friction and noise. Integrate out small volume detail and you get a coarse-grained field. Every ensemble here is 1 act of not asking, and each buys the same thing, a smaller, more legible problem whose discarded couplings reappear as its cost. The free energy is the price of the coordinates you decline to follow. This section explains what quantum statistical mechanics reduces to once you remove particle interactions. Strip the interactions away and the subject collapses to bookkeeping. How many indistinguishable particles occupy each single particle energy level? The only quantum residue is the symmetry of the many-body wave function. That alone cleaves the world into 2 kinds. Bosons, which crowd, into 2 kinds. Bosons, which crowd, and fermions, which exclude. Everything exotic the chapter reaches is the same move seen through a different lens. Black body radiation, Bose condensation, the electron gas in a metal, each one is a single occupation formula evaluated on a different spectrum. The arc of the chapter is a descent by simplification, abstract down to concrete. First mixed states, then the harmonic oscillator, then indistinguishability, then the non-interacting cut that renders everything after it trivial. This is what Chapter 7 is for. Learn the cut, and you regenerate each application yourself. Learn the cut, and you regenerate each application yourself. This section explains quantum statistics as a single binary applied everywhere. The one question is whether two identical particles can occupy the same single particle state. Bosons can, fermions cannot, and that lone bit regenerates the whole chapter. The move that makes it tractable is to stop tracking the many-body wave function and count occupation numbers of single particle levels instead. The interacting mess collapses to independent modes, each one filled according to Bose-Einstein or Fermi-Dirac. From that one contrast fall black-body radiation and Bose condensation on the boson side and the Fermi sea of metals on the fermion side. The chapter's arc runs from abstract to concrete, through simplification, mixed state, then non-interacting, then occupation number. So you predict any new case by asking only how its particles share. This section explains where the book stops deriving relations that hold, no matter what the solution is, and hands you the two ways to compute a partition function that almost never has a closed form. The partition function is almost never computable in closed form. This chapter is where the book stops deriving relations that hold regardless of a solution and gives you two ways out. The first way is to sample the Boltzmann distribution instead of summing it. This is Monte Carlo, a Markov chain rigged so that its stationary state is equilibrium itself. The second way is to expand around a limit you already solve, adding small corrections term by term. The generative move is the one that recurs wherever a sum resists. You replace the exact total with the convergent process that reaches it. And here is the understated surprise from Chapter 8. When the expansion fails to converge, that failure carries information rather than marking a defect. The radius where the expansion breaks is the phase boundary itself. This section explains what remains possible when the partition function will not integrate, which is the generic case, and it makes the claim that two moves exhaust the practical space. The first move is to sample the Boltzmann distribution instead of summing it. This is Monte Carlo, whose legitimacy rests entirely on a Markov chain converging to that distribution. The second move is to deform a solvable limit and track the corrections order by order. This is perturbation theory. The turn that does the real work is this. The second move's failure carries physics. Where the theory stops converging is exactly where a phase ends. Analyticity and the phase boundary are the same wall. One object, the Ising model, carries every instance the rest of the book will need. This section explains how a phase of matter is fixed by the symmetry it broke, and how topology forces its defects. Forget the atoms. A phase of matter is defined by which symmetry it broke, and the entire zoo of its rigidity, excitations, and defects follows from the shape of the space of equivalent ground states it could have chosen. That space, the order parameter manifold, is a quotient, all degenerate orderings glued together. The order parameter is a map from physical space into that manifold. Wherever that map cannot be combed smooth, topology forces a defect, a vortex, a dislocation, a domain wall. Magnet, crystal, superfluid differ utterly in their atoms, yet share defect structure whenever their manifolds share topology. Universality is the same homotopy group, counting the same knots. Predict the next phase from its broken symmetry alone. This section explains what classifies a phase of matter. 3 states of matter became hundreds, and cataloging collapses. Sethna's Chapter 9 hands you the generator that replaces the catalog. A phase is classified by which symmetry it broke, not by what it is made of. The high-temperature state has some symmetry, rotational or translational, that the ordered state cannot keep. Broken symmetry is the sole classifying invariant. Everything else is forced downstream. The order parameter is just a coordinate on the manifold of equivalent broken states. The low-energy excitations are the cheap motions along that manifold. The topological defects are the ways the manifold wraps that cannot be smoothed away. 4 steps: symmetry, order parameter, excitation, defect, but one primitive. Name the lost symmetry, and the phase writes itself.